We've seen that suffix trees solve all these problems in theory, but have large overhead, especially in space. What we'll discuss now is the suffix array, which is a data structure that tries to put suffix trees on a diet, essentially get the same types of algorithms that we could implement on suffix trees, but using something that's more friendly to implement, will be basically based on arrays, as the name says, instead of pointered structures. And in the same vein also gets rid of lots of the overhead. All right, I want to present at least the idea today. Here's again our favorite example string and its suffix tree, but it's drawn in a different way. It's drawn, well, first of all on the side, but okay, you can tilt your head and then it looks normal. I did this on purpose because then I had space to expand the labels, the suffixes in the leaves. Remember, the suffix tree really just stores the start index, but it represents a suffix of the text. Goody. Moreover, I have some freedom in the tree in which order I list the children of a specific node. But a very good convention, and one that I want you to follow, otherwise you will get trouble with the tutorial questions, is to list the leaves in lexicographic order, or to list the children. The $sign is always assumed to come before all actual alphabet characters. And then I'll just assume normal alphabet order. So A comes before B, and B comes before N. Okay? And we can do this in all the nodes. So B comes before N, dollar comes before A, etc., etc. If you do this, and now you read your leaves, well, left to right as it was, now it's top down, you will notice that this is a sorted list of strings. It gives the suffixes in sorted order. Okay? Just to be on the safe side, we know what lexicographic order means. It means like you search in a dictionary of words. So one string is smaller than the other. Well, if the first character of the first string is smaller than the first character of the second string, the first string is smaller. If that character is bigger, then it's bigger. But if they're the same, you keep comparing the next character. And if you append this dollar to all your strings and make it smaller than all the characters, you ensure that shorter strings are sorted before longer strings where they appear as a prefix. That's the standard way how words in a dictionary, I mean, I'm talking about dictionary, German, English, English, Latin, whatever, German, French. The words are sorted in that order. That's why it's called lexicographic, like in an encyclopedia. They use the same. So the suffix trees, if we use this very useful convention of listing the children in the right order, they happen to have this property that they give us the suffixes in sorted order. That's just an observation. So the idea then is, how far do we get if we only keep this sorted order of the suffixes and we forget about the tree entirely? In essence, that's the suffix array. So remember again, these are not really strings. These are just the starting positions of the suffix. So the only thing we have to store for representing this list is the starting index of that suffix in an array of all the leaves. So I use L for leaves, and it will have a second meaning of going left that you'll see next time. And this is the suffix array. It's the starting positions of the suffixes or of the leaves in lexicographic order. That's all it is. And even if you have exactly that and nothing else, we can actually do string matching on this text. Suppose we have a text, we compute only this, the suffix array, and now we're given a pattern P. How can I find whether or not this pattern occurs in the text, and where if so? The key point is it's a bunch of numbers that mean nothing, but if you expand them to the suffixes, it's actually a list of strings just written very concisely. Okay? And that list of strings is sorted. So we can use binary search on this sorted list. In particular, if we search for Anna, our favorite example, I guess, what would binary search do? It would probably start in the middle, and it would compare the key we're searching to the key at that position. Anna is lexicographically before this, because Anna is shorter than this, but it appears by coincidence at the first position, it appears as a prefix of the suffix there. That would mean binary search would now cut this in half. So we've gone from this range where occurrences could have been, we've narrowed it down to that range. That's how binary search works. It's the same as in binary search trees, but we apply it on a list of strings now.
In this case, like, we can only look for the string which are having the number less than 3.
You're saying we can only look for strings that have a number less than 3?
List that we have made, if it's less than 3, we just have to look for that one, because the Anna's the count is 3, so we just have to match 3 afterwards.
Oh, I see. You mean in this comparison, so this first comparison zoomed out would compare, is Anna smaller, bigger than Anna ban? Anna, there's one too much. Anna ban. This is really hard. How would the comparison go? It would compare the first character, same, second character, same, third character, same, and then we run out of pattern, which means it's smaller by convention. So in that case, we would say this is the answer.
No, what I'm saying is, for in case like where 7 is written, and we have to find Anna in it, so we'll not look into the 7 one. Like, we'll directly look for the places like where the number is less than 3, because the minimum, the pattern that we have to match, the minimum combination is 3.
OK, you're saying we could try to avoid this comparison because Anna is longer than what we're looking at here.
Yeah.
This is not how binary search works, though. You're trying to outsmart the method, but this is not how binary search works. It doesn't know how long the strings are, and it doesn't really care. Maybe it could. But in this small example, it happens to be that we pick up very, very small suffixes at the end. Those are a small fraction. Usually, think of a long text and some moderately long pattern. You would mostly compare with longer suffixes. I mean, that's a weak argument. At least nothing breaks if we just continue like this. So we do the same thing again. We compare Anna with Anne. And now we find it's bigger because the first characters match. But then this has reached the end and this hasn't. So we sort that before. And in that case, we have narrowed it down like this. And the binary search would keep going. And it would find the position where Anna would be inserted if it was in this list. OK? And it would have to go here. That's where Anna would belong if she was around. We can do a second search for Anna plus a character that's bigger than all the other characters. That would give us this position. That's the end of the Anna interval. As you might notice, the two strings, the two suffixes that start with Anna are next to each other in the suffix array. And they have to be next to each other in the suffix array because the thing is sorted. So if that occurs as a common prefix, all those strings are adjacent in the sorted order. So what we can do is 2 binary searches bring us exactly that range. The first one is a standard binary search for finding the insertion position of Anna if it was in the list, or if it wanted to be in the list. And the second is modified so that it finds, well, just behind Anna and nothing else. So with 2 binary searches, 2 searches really show us the interval of positions where this pattern occurs. And if that's empty, it doesn't occur. If that's not empty, you find all the positions where it occurs in exactly that space. OK? OK, what else? OK, if we count the number of comparisons we need for those 2 binary searches, you get log n from the binary search. You have to cut things in half log n times before you add a single element. And each of those comparisons with the string takes at most m character comparisons, because you have to walk, well, that way. You have to walk through the pattern and compare characters. The worst case is that you match all the time, and then until you get a decision, you have to read the entire pattern for every single comparison. So you see, this is not quite as good as suffix trees. Suffix trees could do the same in theta m time. Now we need theta m times log n. But then on the positive side, we didn't need all that crappy tree. It was completely irrelevant for finding the matches of a pattern in the text. And all we had to store is a single array. That's much sleeker than this fat suffix tree. OK? And we'll explore next time how to do this structurally, what else we can do with suffix trees, suffix arrays, and eventually how we can construct them.